Hello everybody. Welcome to the stream. Yeah. Oops. Supposed to be some. It's supposed to go down. Up. This should be right. Okay, welcome to the stream. Today we're gonna study computer network. Hooray! Computer network. Reopen. Yay! Computer network. Okay. So I think I need to update some things. Hey, update. There's nothing to update, so yep. Okay. University year 2 semester 1 computer this. So I might have a clock. Timer. Okay. And yeah. Is this too big? I think it's alright. So I might go up here a bit. But like time, stopwatch time. Work and break time. Pomodoro? Yeah, Pomodoro is nice. Windows. You have Mac. Let me get this one. Okay. So yeah. So I need to add to here. Introduction to IT. Principle of statistics. ABAC? What the hell is this? No. Should delete the ABAC thing. Okay, so delete repository and then like here. Okay, and then yeah, pretty much it. Not this one. I have to remove this. Yep, and then okay, so where's this application? No, I need to do security and then allow open anyway. Yes, open. Way. There we go. Hooray, hooray, hooray. Hip hip hooray. Pomodoro, you're here. There you go. I think it's too narrow. Maybe that's all right, I think. Yeah. Yeah, that's good. So I want to change the settings a bit. Change settings a bit. Settings. Okay, login. Doesn't float. Login. It's directing to here somehow. Hey man, what's the plan today? Studying computer network today, and yeah, computer networks. Yeah, that's the plan. So if you don't know computer network yet, you can stay on the stream and you could learn with me together, because I'm basic pretty noob at this stuff too, so it would be a good opportunity if someone don't know computer network. Apparently, what the hell happened? I don't know. What is this? Okay, click here. Click. Okay, got it. Got it. Click here. Okay, so login here. Okay. Click. Yay. Nice. Okay, good job. That's what I want. Then you go right there. Let's make it smaller. Smaller. Shrink the size. I'll go up here, and then right there. Then yep, right here. Oh, god damn it! I forgot. Never mind. I have to set the settings. So this would be like how many minutes? 90? Actually it's, oh yeah, actually I don't need this. I can just use clock. Yeah, it's clock. Alarm clock. 45 is good. I have studied at university classes, but teacher can't explain. It kind of sucks. Yeah, same. Same here. So now 30. I would like to have a clock here. This cannot shrink. Stopwatch timer. Yeah, maybe from App Store, I think. Stopwatch. This one? Yeah, this one is good. This is digital. Never mind. Does it work? Let's see. Maybe. Maybe yes, maybe not. Who knows? Okay, you have the flip clock. Can you go smaller? Is it this much you can go? Give me this one. Done. Okay, and can you... Oh, it's just a clock. Dang it. I guess I'll just use this clock then. You know, let's keep it here. Let's make it smaller. Can't go even smaller than that. Okay, that's good. So it'll be just okay. So let's start today. How was your day, by the way? Was it alright? Was it fun? Not fun? Hope it was fun. So yeah, we're gonna study computer networks today, and yay. Around here is fine. Okay, so we have this thing. We have an Indian teacher. Note means love his accent though. We have an Indian teacher teaching us computer network. Awesome teacher, but have trouble understanding him sometimes. So I'm gonna do something. Update. Okay. Let me get some water and then we'll start studying. Hooray! Oh.
You know, computers or a switch or a router, whatever node, it can be a node, okay? But how to connect two nodes to form a network, that's the question. And here we have cloud computing. Cloud. What is a cloud? Cloud means network. Many computers connected with the router, switch, and they can exchange messages. That idea is called a cloud. So the cloud is just an abstraction of a huge network. We use the word cloud. Cloud means easy word, easy. You say, I'm using cloud for computation. Easy. But actually, it is very complex. Okay? So a complex word in cloud is just abstraction of a complex network. Okay? Yeah. So here the problem is how to connect computers to make a network. So we are using the word link. Link means connection. And in the previous class, we have seen a very model. Hey, this is the updated slide you can download from the MS team. Okay. The old lecture 2 slide was not updated. I changed now. So we need this information. Network are based on a pattern or a principle. That is what OSI model is, a 7-layer model. Starting from here, physical layer, data link layer, network layer, transport layer, section layer, presentation layer, application layer. We have seen the previous class. Okay, this is the basic model of a network. But the whole network, different network, they don't have this model. But especially internet. Internet, what happens is it will never follow the 7-layer. Out of 7-layer, it will follow only 5 layers.
It's only follow 5 layers. So OSI model, okay. So this is the way you communicate. Okay, so why do you even need OSI model? So my question, why? Okay. That's only audio, bro. Yeah, that's only audio, man. I recorded it's from the lecture that I did just 4 hours ago, and I record his voice, and we have some slides. So yeah. So first thing is he talked about OSI model. So I'm not sure what is OSI model yet, but I think if you open App Store, what's update, AS Place update. Okay, so we have an OSI model like this. So we want to know why, or what's the purpose of it. OSI model helps users and operators of computer network. Why is OSI important? Exactly. Determine. Okay, let's see the first one. Oh, I need to I forgot. I need to put the thing. Yeah, totally forgot about that. So what is OSI model? And the Open System Interconnection Model describes 7 layers of computer system coming over network. Hey, yo, Tân Khao and Joy to Live. What's up? I haven't seen you for a while. However, the OSI layer is still widely used as it helps to visualize and communicate how network operate. Okay. Here, OSI model explain human computer interaction in a way application can access the network, ensure the data is stable, Oh, I see. I see. You need the token, I mean the OBT, right? Ensure that data is unstable format and it is where. Ensure the data is in usable format and is where the data. Okay, maintain the connection. Transmit the data using protocol TCP UDP. Decide the physical part of the data take. Define the format. Okay. Yeah. Well, what's, oh, it's opening. Whoa. Okay, that's good. So okay, but why do we even need? I know that this is like the thing, application and stuff. Advantage, yeah, to help users. Okay.
$5,000. Okay. The program is simple. It's client. Now the server.
Nice. Okay. So basically, OSI model is a diagram to visualize how a net how does the network works. So it's nothing but just a visualization, I think. So and then like, yeah, that's what I understand. Okay, so why? servers in C. I'm going to go bring some popcorn. Standardizing a network system and assisting in troubleshooting server network. And assist. Okay, so OSI is for standardizing network system, so having a standard protocol for it, and also it helps to visualize and understand the network. So basically these things are, I don't know why it's even important, but it is helpful framework for equipment manufacturer that enables to them to, okay, this one is good. So what is this? We know this is this thing. Why does it matter? Yeah, so establish a standard communication protocol is key for formalizing communication across external and internal networks such as the cloud and internet. Okay, it allows to define the standards. Standard for manufacturers. Mobile OS is key for network devices. Modem routers, I see. Administrator can troubleshoot the problem in a specific layer. So it's like just crucial for it's crucial for designing and manufacturing and troubleshooting. So oops. Okay, so OSI is an open system interconnection. You may ask, why do we even need this, right? I have the same question too, but from my understanding, the 7 layers are these, right? Keep in mind, I'm also a beginner in this in this study, in this subject too, so it's from my understanding, all right? So OSI, there's 7 layers, and first layer is application, where people can use how do I say, people can use web browser, HTTP stuff, right, for web browsing. Second layer is for encoding the data and stuff. So once you send a request, it goes to the 6th layer, which encodes your data, compress your data. All right, once it goes there, it goes to session layer. Session layer is for it's basically, session layer is, it attach IP, I think, IP address to the packet. It attach IP to your data or your package, so that your packet knows where to go, which computer to go. And then once it's done, it goes to transport, and then transport will break down into segment, and then it will see, oh, which way is the best way, or which track should I go, if I receive the data correctly or not. It will do a bunch of checking here, and it will see like, oh, which pathway to go and stuff, right? The third layer is one, it breaks your segment into package. Oh, it was segment, sorry, I misused the word. It's like basically you get a segment of stuff, and then it breaks into package. Once you break into package, it will know which route to use, and then it will start destination node. Yeah, so I quite don't understand session. Creates communication channel. Okay, my mistake. So if you go back, session is for creating a communication channel. Like, oh, so there's like 3 channels, and they're like, oh, you go in the second channel, you talk with that guy in the second channel, something like that. And then in a network, you attach the destination node, like such as IP here, IP, internet protocol. And then the data link layer, what you do is you break package into frames, and then you send it to small package. All right, so basically, when you send a package to some computer in the network, the package might be corrupted. So what I mean by corrupted is that, for example, if Joy to Live send me a file, all right, on the way sending the file, there might be a lightning strike, right? And then the bit might change, because essentially when you're sending a file, sending something to the internet, you're sending a bit. So once if the bit is corrupted, then you won't have the proper file, you know. So what it does is, data link, I think it does is like, it checks the error, it synchronizes, so that if error happens, it will send again and again, or it will let the end user know like, oh, this file is not correct, I'll send you again, or blah blah, right? It happens all underneath very quickly. And the physical layer is the hardware, where you actually send zeros and ones, like from the cable Ethernet. So that one. So this is the brief explanation of OSI. Okay, so why do we even need, right? We need because so that we can standardize the network system and assist with troubleshooting. So standardize means manufacturer will use this protocol to make their router, modems, or switch and stuff. Okay. Second, it's also needed for us to visualize how it works. So you can visualize and understand how the network works by using this 7 layer. Okay. Third is so if you are a network administrator, you can actually troubleshoot the problem. For example, let's say that you want to let's say that your router have some problem in the physical layer, right? So rather than going and fixing all the up layer, you can just fix in the physical layer. So if your if your cable is if there's something wrong with your cable, you can just plug it in and plug it out. So it is kind of separate design, you know. If something wrong happens in the data link, you can actually go to the, like, let's assume that there's a data link code or something. You can actually go to the code and fix it. If there's a network layer, you can actually go to the network layer and fix it, you know. So if there's a TCP problem, yeah, that might be a code problem, you can actually go and fix there, or somehow, you know. So there's a separation in the layer. So once something wrong happens, you can actually go fix there. Yeah, so this is basically OSI thing. So yeah, actually this is really good. So I'm gonna keep it here. So yeah, so that is OSI, and we also have internet model. So what happened is that in the internet model, we don't have the 7 layer. So internet model. In the internet model, we don't have this 7. We just have 5 layers. So why do we have 5 layers? So you can see, right? 1, 2, 3, 4, 5. There's 5 layers in the internet model, which is different from OSI, Open System Interconnection. So internet model layer, yeah, or you can call it TCP/IP model. Yep, or other name is, you can call it TCP/IP model. So let's see, TCP/IP model. So TCP/IP, yeah. Okay, so ouch. So TCP/IP model, the OSI model we just looked at is reference and logical model. It was designed to describe the function of communication system by dividing into TCP/IP was designed and developed by Department of Defense in 1960s. Space Standard Protocol. It stands for Transmission Control Protocol or Internet Protocol. The TCP/IP model is console version. Console. What does this mean?
Concise.
Concise, or giving a lot of information. Concise version of OSI model. It contains 4 layers, unlike 7 layers. So TCP/IP contains 4 layers. All right. The number of layers is sometimes referred as 4 or 5. In this article, we will study 5 layers: the physical and the data link layer, as reference to one single as physical layer or network interface layer. Okay, so you can combine these two. What does TCP/IP do? The main work of TCP is to transfer the data from a computer to another device, to another. The main condition of this process is to make data reliable and accurate so that the receiver receives the same information as sent by receiver. Okay, to ensure that the message reaches the final destination accurately, this model divides the data into packages and combine them at the end, which help maintaining accuracy and data transfer on it. Okay, so what is TCP/IP, huh? So we have to know this part. Okay, so what so TCP/IP main work is to transfer data. Its main work is to transfer data from one node to another. Okay, the main condition of this process is to make data reliable and accurate. Okay, ensure that much. And then once it's doing this, it's divides data into packets, and combine. Okay, so my question is that how does the TCP/IP model works? I want to know. How do you send it? And how? Okay, so let's see TCP practical.
So let us try to understand the relationship between different layers of the TCP/IP stack with the help of a real-world analogy. So suppose we have this gentleman, and this gentleman has packed his luggage because he has decided to move from his current residence to a new residence which is few miles away from his current residence. And for the purpose of transportation of his luggage, he has hired a courier company called Movers and Packers. So let us try to map various elements of this situation to the TCP/IP stack. So this gentleman who is looking to be transported to his new residence is an application, and his luggage is an application data.
What? Oh, I thought he just said that and then sell his cost.
And his luggage is well packed so that it do not get damaged during the course of transportation. So this function can be mapped to the session and presentation layer, because the session and presentation layer is responsible for encryption and decryption of data so that this data cannot be compromised while it is on the journey over the network. The courier company is equivalent to the transport layer. Now in the transport layer we have two famous transporting protocol, which is TCP and UDP. So if this courier company takes the responsibility to safely transport your luggage to the destination, then this courier company behaves as a TCP protocol. Otherwise, if the transport company do not takes the responsibility about the safety of your luggage, then this courier company behaves like a UDP protocol. So this courier company is responsible to transport your luggage from your current residence to your new residence, and therefore this courier company acts as a transport layer. The new apartments which this gentleman is shifting is like a destination IP address. Now coming to the road can be thought of as a network layer because road is a path from your current residence to your new residence. So network layer is actually responsible to take your data from source machine to the destination machine, and finally the various traffic signals which the vehicle will encounter on the road can be thought of a data link layer because the vehicles passes through these traffic signals in a hope by hope fashion. So this is a good real world situation where different entities in this situation and the
So, all the segment.
Yeah, but I want to see how it's implemented.
Communication for network S.
So here we have two files, server dots. So now we will define some variable and structures. If we have
Bang! You're getting banned. Where's that? Timeout. Timeout. There you go.
have two pieces to make a pretty good tutorial. Let's reply this. So like nothing much. Okay, so that's it for today, guys. This is what we'll be looking at. This is a really cool stuff that on a simple code that we have written, we are able to use the functionalities of the computer like ports and sending a data stream over the ports. So in next tutorial, I will get you through the introduction of what actually the prerequisites are for TCP programming, and then we will start coding. See you guys, JJ here. I hope you would like, subscribe, and okay guys, welcome to tutorial number 2 of socket programming. So let's start to understand this code. So we'll be going through the theory, the prerequisites of whatever this code requires. So first of all, first things first, let's see the hash includes the files we required to write this code. So we see quite a lot of files out there. stdio.h standard lib. I want you to read those files: sys.types, sys/types.h, sys/socket.h, and netinet/n.h. So a lot of files, and right now we don't know what they mean. So first, let us know what they mean so that we can really understand the code. Okay, so let's see what these files actually. So well, I have just prepared a table for you. So let's go through and see one by one what each file do. So the first file we have is #include sttio.h. So if you're writing a code in C, you basically can't do without sttio.h. sttio.h means std is standard, I is for input, and o is for output, and .h signifies the header file. So #include stdio.h, you will be requiring this in most of the codes you write in C language, wherever you want to use input and output functions like printf and scanf, which are quite a necessity in all the C programs which we will be writing. Now the second file is #include sys/types.h. So what sys/types.h means is it's a system file, and this header file contains definitions of a number of data types used in system calls. So basically what this file does is this file will help execute these two files. These two files are very important for our program, and for these two files to function, that's the socket.h and netinet.h, we require types.h. So types.h is like a father to both of these files. Structure contains so that we can use the functionalities of our compute data coding. We require one more session for tutorial, guys. Get the ground running, and welcome back, guys. So here accept.h to the socket referred by analog display. Okay guys, welcome to.
What the hell? Okay, never mind. These are my questions. AP soft.
I'll say this, Chris. I mean, in the CCNA, as an example, they teach a little bit about TCP. It doesn't go deep as perhaps we'd like for the real world. So I'm really looking forward to you showing us how this actually works in the real world. Hey everyone, it's David Bombal back with Chris. Had a lot of great feedback from our I'll say this, Chris. I mean, from our previous videos. Chris, welcome.
Hey, it's great to be back here with you, David. Thank you for having me back.
Yeah, so what are you going to show us today? Because I'm quite excited about this topic.
Yeah, so we had a lot of comments, like you mentioned, for the last couple of videos. So I thought what we could do is just back up a minute and take a look at some TCP concepts. Learn some core TCP, things that will help us to be better troubleshooters, better analysts, and even better hackers if that's what we're getting into.
Let's get straight into it, and then I'll ask you a bunch of questions. Now, for everyone who's watching, please put in the comments below the kind of stuff that you want me to ask Chris on future videos, stuff that you want to see. We want to create a whole bunch of videos, including a series on TCP. So see this as like the first video in the TCP deep dive series, but let us know, questions that you've got. And Chris, is it true that you're going to give us the trace files and I can put them below? Is that right?
Yeah, absolutely. You can hit the link in the description down below and you can follow right along. I think that makes it a bit more interactive, and we really encourage you to do that because I think all of us, we learn by doing. We retain better when we actually have our hands on it. So we encourage everybody to do that.
That's great. So you take it away, Chris. Show us your trace file and let's start with the beginnings of TCP.
So I think this is a great place to start, David, because how many of us, okay, let's go from the networking background, right? You come from the networking background, I do as well. How often were you blamed for network problems?
It's always your fault. Come on.
Right? Oh, it's slow. It's the network. Oh, it's not connecting properly. It's the network. It's the network. I think it's kind of funny because sometimes we'll even make a phone call to our bank, or we're setting up a flight, or pre-pandemic or whatever it was, and you're on the phone and there's like this hold and the poor operator's saying, I'm sorry, my network's slow today.
Exactly.
Have you ever had that experience?
Yeah, exactly. It's you guilty until proven otherwise.
Absolutely. So right there, if we're in the network space, or even if we're just growing in our knowledge of protocols, TCP should be a big part of that. And the reason why I took that down it's not the network conversation is because being a consultant, being a troubleshooter, that's what I do. A lot of times people call me because they're having network issues, or it's the network people and they're calling me and they're saying, hey, I'm getting blamed for this. So what's going on? But then I look at the trace file and I start with the transport layer. Why? Because I can then take the OSI model and I can break it in half. If I start looking at TCP, and TCP looks healthy, I don't see delays, I don't see any weird TCP indicators at that layer, well, then I can go up and I can take a look at the application. But if TCP is not healthy, if I see retransmissions, out of orders, window problems, blah, 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 those kinds of things, or especially with retransmissions, okay, now I can go down to the network. Why is the network dropping traffic? Why are things not being pathed properly? What kind of hiccups are we having in getting data through? So that's why, David, we're going to start here at the transport layer, specifically with TCP. This is why it's such an important thing to understand for troubleshooters, for network analysts, even cybersecurity professionals.
I'll say this, Chris. I mean, in the CCNA, as an example, they teach a little bit about TCP. It doesn't go deep as perhaps we'd like for the real world. So I'm really looking forward to you showing us how this actually works in the real world, and I want to quiz you on like all these different flags and things. So yeah, looking forward to it.
Fantastic. Okay, so good. So let me ask you this, David. When it comes to the TCP handshake, is that something that you would be quizzed about on your CCNA?
Yes. So yeah, I hope you're going to explain the three-way handshake in proper detail with a proper Wireshark capture.
Absolutely. So let's do it. So here I've got a trace file open, and we're just going to spend some time on the handshake. Only we're going to spend enough time to go into the detail to really understand what the handshake is doing. What's the purpose behind it? It's way more than sin, ac, ac.
Because that's what most people know it for, yeah.
We passed that question on our CCNA. Good. Sin, ac, ac. Wonderful. Why is it called sin? What's happening in that handshake? Really, why was that term selected? What is an ACK? What are we ACKing? Let's get to it. So if we take a look at this PCAP, and again, everybody go get it, go download it. And the one you're going to make sure that you're on is TCP handshake.
Wireshark. Go deep. I want to build it from source, man. Let's get the source file. Let's get the source. I want this documentation. One single page. Oh no. A multiple page. Whoa. One single page. Boom. Whoa. Whoa, documentation, all. This guy is legend. Wireshark. Show me left. Wireshark. Okay. So we want to build it in the thing. Programming. Show. So we have Wireshark. Okay, so how do we have cat read me, yeah. So how do you build? Okay, installation, okay. Whoa. What? So many things. Why there's so many things? Easy.
And
Wireshark.
I think that it's way on RCCNA. Good. Really, why was that term selected? What is an ACK? What are we ACKing? Let's get to it. So if we take a look at this PCAP, and again, everybody go get it, go download it. And the one you're going to make sure that you're on is TCP handshake.
Open. Oops. $. Download. Can't I just drag and drop? Much easier. There we go.
And I threw my name on there just so you knew that it was me. Here, this first packet that's going out, this is only a 15 packet trace file, right? So this is not a big one. This isn't just some long, huge TCP thread. And really the way that I captured this is I just opened up a browser and I went out to this website that's open. It's a website that's designed to be just over HTTP. I wanted to make sure this wasn't encrypted. It's just a very simple conversation over TCP. But what we're going to focus in on, let's go ahead and get into that handshake. I'm going to take a look at packet number 1. This is just the first packet in the trace. This is the first time that this station reaches out and establishes or tries to establish a connection over TCP. Let's see what's going on in this packet. I'm going to go ahead and move my detail up a little bit, move my hex over just to see, head check to see if I have any clear text over here. Of course, you know, in the SYN, I'm not going to see any data, but I just wanted to see what we have over there. I'm just going to move this back. Okay, so in my detail, I'm going to skip over layer 2, layer 3, which would be Ethernet, IP. I'm just going to go straight to layer 4. Now, first thing, I can see the client is sending, it's starting from this high number source port. We call this the client side ephemeral port. Usually this is a pretty big number like you see here. Right away, when I just see that, I wouldn't even need to see this up here. Usually when I can see that information right here, I'm going to destination port 80, I'm coming from this high numbered port. Right there, I know that, okay, client is sitting on 54846, the server's on 80. Port 80 is going to be a common number. It's going to be a well-known port number for that service. Okay, great. The next thing that Wireshark does for us is it gives us something called a stream index. What that means is basically it's the 4 tuple for this conversation. What's a 4 tuple? 2 IPs and 2 port numbers. That gives me a unique TCP conversation. So Wireshark says, hey, this is number 1, or in this case, it starts at 0. But the first TCP stream that I see in this trace file, this is 0, and this is all just 1. If I saw a new 4 tuple immediately after this, let's just say, David, I saw 2 SYNs go out. SYN. Well, then I would see stream 0 and then stream 1. Okay, moving down, let's go ahead and talk about this sequence number thing. Okay, so here's sequence number 0. Relative sequence number. The reason why this is called a SYN is because in the handshake, I have to exchange, if you will, or synchronize the sequence numbers of the 2 sides. So this raw sequence number that you see here, this big, scary looking number, this is a very important number to TCP. All right, so when I send my SYN to you, David, I'm telling you, hey, I'm going to start counting the data in my direction from this number. It's called the ISN, initial sequence number.
Just randomly selected, yeah? Or how is it chosen?
Yeah, it is a somewhat random thing. Their operating systems, at least historically, they'll typically start in a certain range. I mean, I can't spout that off the top of my head and go, hey, well, you know, this must be a Mac system or something like that. But a lot of times you'll see them start in certain ranges. The idea here is it just has to be unique, right? And it's a number that's randomly generated. It's a high number. It's very unlikely I'm going to see this again on a different connection very near in the future, right? That number, I offer that to you, and then Wireshark just does me a solid. It just says, hey, let's just zero this number out, because we talked a bit about this in a previous video, how Wireshark goes, you know what, you humans have a hard time counting with big numbers. Why don't we go ahead and just zero this out for the purposes of this connection? So that's why we see sequence number 0, relative sequence number. Good with me so far?
Yeah, I wanted to ask you some questions. So let's start with the port numbers. So the source port is like a random port number, or ephemeral port goes by different names. I can't remember the ranges off the top of my head, but it's a high number, isn't it? And then like the greater than 1023 or 1024, depending on which operating system you're using. I think, Chris, that's the thing. I mean, you've got a lot of experience doing this in the real world. Different operating systems handle the port numbers, and like you said, the sequence numbers differently, don't they?
Yeah, they do. And really, when it comes down to it, something just when we're getting started with this, just to remember that as long as this isn't the same, right? So if I start a connection to you, David, I got to use 54846. If I want to start a new connection to you, well, then I can either increment it by 1, depending on the operating system. It might be random. I could jump up to 55900 or something like that. But the point is, as long as it's unique, then when you are communicating data back to me, my machine knows what to do with it, right? That port now gives me a place to stick that data that the application can use. So there's something that happens in the handshake, and this is where we're going to start to deviate from the simplicity of SYN-SYN-ACK. This is what's actually going on under the hood. You notice my next sequence number is 1?
Yeah.
What this means is that Wireshark is telling me, this is a Wireshark value. Anytime you see these hard brackets here, that's Wireshark giving me information. This is not actually a part of the protocol itself. This is Wireshark doing me a solid. You see it up here, TCP segment length, stream index. The port numbers are a part of the protocol, so is the sequence number, but this is just extra info that Wireshark's helping me out with. But it says sequence number 1. So what happens when I send you a SYN, okay, you're gonna be the server, right, David? I'll be the client. I send you a SYN, hey, Mr. Server, here's my starting sequence number. And there's an action that you're gonna take when you respond. You're going to add 1 to the sequence number and respond +1. What that does is it allows me to know that you heard me. Yeah, in the handshake, it's called a ghost byte. It's not a real byte of data. It's not a true actual byte that I needed to send. But what you're going to do is you're going to increment the sequence number by 1, and then you're going to send me back an acknowledgement number +1. So let's do this. Let's just remember this 7413 right here, okay? Take a look at our SYN-ACK. I'm just going to come down and take a look at the acknowledgement number in the SYN-ACK. So 7414. Okay, I'm going to do that again. All right, let me go back up to my SYN. $74.13 here, and then you come back and you say ACK, but +1. All right, so what does that do? Now, the relative ACK number is a little easier to use. You're just taking the 0 I sent you, the quote-unquote 0 from a Wireshark perspective, and you just added 1 to it. So what do I know now? If I'm a client, first of all, this SYN-ACK just gave me a bunch of information. David exists. I can route to David. David heard me. Right? He's got space available on port 80. He's got resource to accept a new connection. He went ahead and added 1 to the sequence number I sent him. So we're synchronized. As far as I'm concerned, you just act my SYN. I'm now good. I'm now perceiving that you're there and we can chat. Now there's more going on beneath this, but I'd like to stick on this for a moment just because it's so important. So you can see the amount of things I've learned. What else have we learned from the SYN-ACK that you sent me? If I come up here, let me take a look at my delta time. My delta time is the amount of time I have this set up in Wireshark. It's the amount of time between packets. All right, now that's something that's pretty simple to set up. This is something you want to make sure you do in Wireshark. I'm just going to come up to Wireshark preferences. If you're in a Windows system, we're going to go to edit preferences. Let me jump there real quick, and I'd like to show you, if I go to columns, all I got to do is I just got to add a column. Let me just go delta. And then for the good viewers, you just come over here to type, and then we're going to come up to delta time displayed. And then once we have that, I just like to, as a style thing, I just like to move this up next to the running time that I have there. I'm going to remove this because I already have one. But basically, delta time is a great column to have when you're doing this analysis. So now what I know, David, is you in time are 20 milliseconds away from me. So that's nice to know. You agree?
Yeah. It's not a server on the other side of the world.
Exactly. Yeah. And in fact, I can take this 20. And what else can I learn about David? Well, I can come down here to IP. I can expand this out, and I can go to TTL, and I can go, whoa, okay, 238. Now we talked. About this in a previous video, but right now I know David, he probably started his TTL, his IP TTL at 255 because this number never goes up. So it's likely he began at 255. Now I can, look at the math on how far away you are, right? You're probably 17 hops away from me. Another possibility is that this started off on a completely different other number, but it's very unlikely. It's most likely that you started at 255. And
what are the numbers that we start at normally? Sorry, for the people who didn't watch the other video.
No problem. 64, 128, and 255 are the most common starting TTL values. In fact, let's test that theory. My machine, when I sent out the SYN to you, let's go to packet 1. My starting TTL was 64. As that packet goes to you, it gets decremented, you receive it, and then you start with a full count TTL, and then on its way back to me, it gets decremented. So we're 2 packets in. You've synced my SYN, you've acknowledged my sequence number, you're 20 milliseconds away, you're probably 17 hops away. Look how much I've learned about you so far, David.
Here's a very basic question, just to step back. Why do we need SYN numbers?
Because that's how TCP is reliable, right? One of our test questions is often it's connection oriented, it's reliable, it's for sure, it ensures reliable transmission of data. The thing about the sequence numbers is that's how I determine, did you get everything that I sent you? If I send you 100 bytes, that will reflect on the number that you act back to me. You're going to add 100 to the sequence number. The sequence number goes up in conjunction with the amount of bytes that I send you. One sequence number, 1 byte. It's just scary because it begins at such a high number, right? If I come back down to TCP, it's just a scary looking number. I'm not going to lie, that my brain does not want to wrap itself around this huge value. So that's why Wireshark says, you know what? Hey, David and Chris, let's just chill out. Chris, let's just act like you started at 0. David, let's act like you started at 0. And then as you both start to send data, we'll increment this. That's why relative is so nice. Okay, David responds SYN-ACK. Now, he doesn't just ACK me. Let me come back down to that SYN-ACK. He doesn't just +1 my SYN, but he also gives me his ACK, or I'm sorry, his sequence number. Now, does this sequence number, David, look anything like this one?
No, I didn't count the digits, but say another big number.
Sequence number, David, look anything like this one?
No, I didn't count the digits, but say another big number.
Another big scary looking number, exactly. They're not even in the same ballpark. Does this sequence number David look anything like this one?
No, I didn't count the digits, but say another big number.
Another big scary looking number, exactly. They're not even in the same ballpark, right? So it could be you're a server and you're starting in a different range of values. The random number that you came up with is just in a whole different world than mine is. The value itself doesn't really matter. You're just informing me what your starting value will be. So you send this big number to me, your next expected sequence number in this direction is going to be 1. That's relative, right? That's Wireshark saying, hey, you're sending a ghost byte with your SYN, right? That false 1 that you send back to me. And now let's just remember this. 5106, okay, there's our value. Let's just kind of commit that to memory, 5106. All right, so what I would expect is in the final packet, see, I now say 5107. I added 1 to your sequence number. And notice too, my sequence number, I'm now at 7414. Okay, so now I'm gonna do everyone a favor and myself a favor, you as well, hopefully, David. I'm just gonna stop using these raw values because they're just so big. This is the whole point. Wireshark's like, let's get rid of these. I'm at 1, you're at 1. Now we've reached the end of our handshake. Anytime I come up here in Wireshark and I see sequence 1, ACK 1, I know that's a successful handshake. I sent you my sequence number, you +1 ACKed it. At the same time, you sent me your sequence number, I +1 ACKed it. We're synchronized.
And the synchronization is so that part of it is to know what the initial sequence numbers are. Yeah, so we exchange that.
Excellent, that's exactly it. So that when I send you data, you can increment the sequence number that you see me start with, you increment it and ACK the number back to me.
Yeah.
I take your sequence number when you send me data and I do the same. Our sequence numbers are completely isolated to our direction, or rather they're direction dependent. What I mean is that I'll never add, multiply, subtract, divide these values. These values will never intersect. There'll never be some mathematical equation. It's just in my direction, we're using this 17796 number. And in your direction, we're using this 205805 number.
And I'm going to ask you all the basic questions that people may have. Is the first one always a SYN? Is the second one always a SYN-ACK? And is the third one always an ACK? Is it always like that?
That's a great question. And the answer is yes. We can't start, for example, on this GET. This is the application sending data. Now let's actually do this. There's an actual payload sitting in here, right? TCP payload, 501 bytes. And there's actual data sitting inside this TCP segment. So I can't just put this 500 bytes out there on the wire and just hope, David, you know what to do with it, simultaneous to processing it and, preparing the response. I first have to set up the connection. So your question was a good one. We have to establish that connection using this three-way handshake for every connection that we establish. Sin, sin, ak.
Over there, the data sent was 501 bytes or something. Is that right?
Yes.
So does the sequence number jump from, did I read that right? It jumps from 1 to 502. Is that right? Because 501 bytes were sent. Is that correct?
Good question. Actually, you know what? I think it's a good idea. We'll stay on the sequence numbers for right now, and I'll get to the TCP options in a minute. So I like where you just went with that. I'm just going to collapse my IP.
It's just that it causes so much confusion because the big numbers and, how do they increment exactly? And I think you said 1 byte is one number. Relatively, is that right?
It is. So let's all go down to packet 4. Now, if we take a look at packet 4, here there's my sequence number, and I'm not going to use this big scary one anymore, okay? So my sequence number is 1. And David, I have a 501 byte payload here. TCP does not care what the payload is. It does not matter to TCP. It's just data. It's whatever that application up there, that application could be anything. The application opened the hatch, threw 501 bytes down, TCP caught it, and now TCP is like, look, my job is getting this over reliably to the other side. So I've got 501 bytes of payload here. So what I do is I say, here you go, David, sequence number 1. I'm starting here at this value. The next expected sequence number in this direction, me to you, the next place I'm going to begin in this direction is at 502, because I just sent you 501 bytes. On my side, I basically jump forward to 502. If there's any more data that comes down the hatch from the application, I'll send it to you with a sequence number of 502. Let's see what you do back to me. 25 milliseconds later, I hear back from the server, and let's check out the acknowledgement number, 502. What do I learn? My data got there.
501 bytes of data.
Basically, when I send you data, David, I'm going to basically hold back a copy of that data, if you will. In my send buffer, I can't clear this 501 bytes out of that send buffer until you act 502. Once you've act 502, I can say, great, okay, 501, get out of here. Now we can make some more room for some more data in here. Okay.
That's why an unreliable link or something can slow the whole process down, because you've got to buffer that until I acknowledge it. Yeah.
Absolutely. Yeah. Imagine if, and we'll get into this in other trace files. Imagine if I don't hear this acknowledgement. Yeah. What do I do then? Well, then I basically have to wait for a timer to expire. I'm like, you know what, David, I put that 501 bytes out there. A timer will expire on this data, and then I will retransmit. But right there, imagine the information that we would learn. Our handshake worked, but that GET didn't. So now where on our network are we losing that packet?
I was going to say, okay, so 502 has been acknowledged. So on the client side, seeing that we're doing the client side at the moment, the next packet that he sends, can you look at the next one? Will it be like some other number? So some other data has been, so it's 534 bytes, is that correct? That's been received from upper layers.
Good job. Yeah, no, this is our next packet, packet 6. And here we can see that the payload is 534. And now that number sounds similar to the 501 that we sent before, right? But remember that the GET, the data that was being requested, and it honestly doesn't matter the application, this was 501 bytes that the client sent to the server. That was acknowledged, and now the server is responding with, this is the actual application response. So the application opens the hatch and said, here you go, here's the response for Chris, here's 534 bytes, get it across to him. So you say, okay, starting at sequence number 1, you send your 534 to me, and your next expected sequence number in this direction will be 535.
And you kept the ACK at 502, yeah? Sorry, go on.
Good job. That's exactly where I was going, 502. It's exactly the spot. I didn't send you any more data. You're repeating that acknowledgement number. Now it's not a duplicate ACK or, that's a whole different situation. Basically, you're just acknowledging that I haven't sent you anything new.
Yeah.
Your sequence number went up, but your ACK number stayed the same.
That's great. And so if you go to the packet 7, we should see perhaps that increases now, yeah?
Yeah, exactly. So yeah, this is why you hit on a good point, David. So this is from client to server. My sequence number is now 502. But now my acknowledgement number is 535. So now I am ACKing the 534 that you sent in your direction. On my side, my sequence number is 502. On your side, we've incremented that to 535. All right, we've both have sent data in each direction. Now you hit on a good point though. This is an empty ACK. You can see on packet number 7, let's have everybody join me there. TCP segment length is 0. I call this an empty ACK. The purpose of this packet is only for you to, or for me to acknowledge your data. I'm not sending anything new. So that's why, the viewers, if you'd like to, this might be a good thing you can do on your Wireshark profile. You can just right click TCP segment length and add this as a column. One of the reasons why I like to do that is because now I have TCP segment length here. Now I can see payload length and not overall packet length or frame length. If I'm looking at it, including the IP header and the Ethernet frame, if I only want to see the data payload and how much data is there, that's where I like to have that as a column. Let me back up. How are we feeling, David? How do you feel about sequence numbers?
Yeah, I wanted to, sorry, Chris, I'm trying to push home this point because we started with a client. So if you scroll down, where's the next one that the client's sending to the server? Because we were at 502, and hopefully at some point we'll see the client send some data to the server. We should have gone yeah, there we go. So 502, we got 439 bytes from the upper layers. So the next sequence number is 502 plus 439, is that right?
That's correct. And that's a good spot. So in this direction, from client, so from me to you, let's take a look at our next get. It's 439 bytes. I start at 502 because that's where I'm at, right? My sequence number has moved to 502 and I haven't sent you anything else in this direction until this point. Now I add 439 more bytes I'm putting out on the wire. The next place I expect to start in this direction is 941. It's 502 plus 439 equals 941. At the same time, I expect 941 to come back from you because that tells me you got my data. So this is why, and actually I just posted this video on my YouTube channel about sequence number analysis, and I go through a bit more practical use cases on how to use sequence numbers and how they increment. Getting practice of how these sequence numbers work is key to really understanding TCP. Yeah. This is why TCP is so much more than a handshake. It's so much more than just sin, ACK. It's a whole lot going on, and these sequence numbers synchronizing is really why we call it sin, ACK, and it's a key part of how the protocol works.
So if you go to 12, we should see that ACK, is that right? Sorry, I just want to wrap this up because I took you on a tangent here.
It's okay. Tangents are not a problem. They're good. All right. So, So I send you 439. And if I come down to 12, there's my 941. At the same time, in the opposite direction, a few other packets were sent. So my starting sequence number is 1726. And then, you see the OK come in, and that's, this is an empty packet. But the next one, you to me, 1726, I'm going to add 500. And the next expected sequence numbers is 22. 26. Now, Wireshark does something kind of cool for us. Let's have everybody click packet 12. So this is the ACK coming from David back to me. And this is empty, right? There's nothing in here. This is just an acknowledgement. The cool thing that Wireshark does, if you notice on packet 12, so he's ACKing 941, my other packet got there. Check out our little checkbox. You see that next to packet 11? Oops. You see our little check mark there? That's a visual way where Wireshark says, okay, packet 12 is ACKing the data in packet 11. So just with my eyes, I can go up there and I don't have to do a lot of this math in there. Like Wireshark saying, don't worry about it. I got the math for you. Packet 12 is ACKing packet 11. So we're good. There's no need to retransmit it. Now I can clear that data out of my TCP send buffer, and then I can carry on with life. Sequence and acknowledgement number is a huge thing that is important to really understand we're using TCP. And it also can really help us get to the root if we have missing data, if we have retransmissions. We're going to be building out this conversation. This TCP series is going to go into this. But having a good understanding of how sequence numbers work is key to understanding retransmissions, out of orders, and other TCP errors that we can see. Let me go ahead and back up to our handshake. We're not done yet. But first I want to check in with David. Are we doing good on sequence numbers?
Yeah, so just to summarize, you and I both pick a number. Let's assume you're the client like we did in this example. I'm the server.
All right, here's something else cool that I figured out you can do with OBS in Advanced Scene Switcher, okay? So I already know that I can adjust an audio source by changing scenes, but what you can also do is you can actually change scenes based on the status of an audio source. And I'm gonna show you what I mean. I'm gonna do that using my stream starting soon screen, okay? This is something a lot of streamers use. They use it to kind of get their audience ready to go. They get themselves ready to go. I know I use it to hype myself up. Okay, so I'm going to show you what I mean here. First thing is I've got a macro set up here, and that is going to look for the scenario for any kind.
Mom camera and have my camera. Okay.
Hello everyone, microphone little unmuted process guys, you all in the next tutorial. Goodbye.
All right, so I've had this question from a few friends. Maybe that's exactly what we're gonna talk about. That's exactly different. And you can see that currently I have two audio sources. I have the desktop, obviously this, and here we don't want to see desktop audio, but we do want to see the microphone working, or vice versa. However, once you're in file settings, then I'm gonna head over to audio. And what I'm going to do is I'm going to disable the desktop audio source, and I'm also going to disable the microphone audio source. You're like, wait, what? Why would you disable those? Well, I'm gonna show you here in a second. So we're gonna disable all of our default audio sources, right? So all of our devices get disabled. I'm gonna click apply.
Hello? Hello? Okay. I think I need a break. Okay. Okay. Hello? Oh, it's true audio. God damn it. I see why now. Disable one. Yeah, there we go. So when it's like this one, okay, that's good. All right, hello.
You and I both pick some number, and then we
Ding dong,
do the
stop, man. Stop.
syntax to just basically to tell each other what our starting numbers are, and then for every byte we send, the sequence number goes up by 1. Wireshark makes it easy by just starting at 0, relative numbers. The numbers are totally independent of each other. It's like two separate streams. You mustn't confuse one with the other. And I think that's what gets confusing, because you look at all those numbers and I find it difficult, like, okay, so which side am I looking at, and which numbers are relating to which? You got to kind of separate it in your mind. Is that true, Chris? And then how in the real world, because you do this stuff all the time in the real world, how do you get your head around all these numbers and data and stuff? Is it just practice, or are there any quick tips?
Oh, that's a good point and an absolute truth. It can be hard to wrap your head around all these numbers, and I think that's where people can get confused. It's easy to get confused.
Look at TCP header. Let me order some food. So hungry. Understand makes sense. I see. Okay. Essentially, I don't wanna I want to I know the theory behind TCP is for transmitting data and stuff, and there's UDP stuff, and I know oh, they will attach the header checksum or some things, but what is it? I know some might say this is TCP, but where is it? I can't see or something, and apparently we can actually see here. That's what I'm looking oh, this is TCP here. I want to see the practical, not explanation oh, we have it's a protocol, yeah, but yeah, so where is it? Can I see physical? Can I look at the code? Can I look something? Yeah, but what? Give me more concrete, checksum flag, what, this. I want something like this, yeah, there's this one, and we have TCP have source, okay. Oh, this makes sense. Source is 80, destination, okay. And this is the data. Where's the data? Not this one. Yeah, this one. This is the data here, And now, three-way handshake. Really, it's not TCP. Yeah, TCP really works. Part of the protocol. I see. So how could I actually see the TCP? I wanna look at something like this, the practical side, not the the theory and stuff.
about TCP. Practice is a big one. Just looking at these flows and really what you and I just did, step through them one packet at a time, and watch how these numbers increment. I'm not gonna lie to you though, David. I'm kind of old school. When someone sends me a PCAP file and I realize that I gotta go down to the TCP road and I gotta do my TCP.
Otherwise shit won't make sense. Yeah, but how about I already understand the theory? Let's assume that I already understand the theory. So what's next? You know?
In-depth analysis. I'm not joking. I get out a big piece of paper and I write client and I write server on the other. And I literally will sometimes have to trace out manually those sequence numbers just
See
to
the theory in action? How? Explain me how? Like yeah, like this would make sense, you know? And then starting explaining from here. But this Wireshark, I see.
keep my head straight. Sometimes, yeah, it gets pretty deep, especially when you're doing multi-point analysis. Sometimes I'm not just looking at a single PCAP from a client. Right here, just with a glance, David, the round trip delay that we're having, the initial starting RTT, we call it round trip time, 20 milliseconds, just by glancing at
C packets for three-way handshake. Check the control flag extractor. Yeah, that's what I'm checking. The flags are here, the checksums, and then the flags, I think it's an option. Where are the flags? I think it's in the no. Yeah, frame. Yeah, flags. There you go. So this will start from the beginning of the data, and then where's the end? What? There's only, oh, this is a start from I thought it was supposed to be like beginning and the end, you know.
this, I can tell you we're capturing client side, right? The SYN goes out, 20 milliseconds later, we get a SYN ACK back. And then boom, the ACK happens only 59 microseconds later. So that's how I can tell what side I've captured on. Sometimes I'm dealing with multi-point captures, a capture that was taken on the client, one that was taken on a firewall or somewhere.
Do you understand how it's communicating? Roughly, I guess. So basically, like, so there's like in the, so I went to a rabbit hole. So I was looking up TCP IP model, which is 5 layers, right? Which is this 5 layer, and this is OSI. So I was thinking like, okay, I understand, okay, the application is the HTTP stuff and all the stuff. So I want to go deep dive into it. So how is it working, you know? And I want to see the code, how did they do it? So I can't find the code. Someone just called. Okay, I'm back. So like yeah, so I went to a rabbit hole. So understanding TCP/IP. Hot classmate no, it was 7-Eleven. So yeah, there was. I knew that from the application. So what I know so far is like there's two models, and like the data flow from application layer to this layer and downwards, and then once it goes to the end node, then the physical layer will open and stuff. But I don't know how it actually communicating. But I know roughly it's like, so once if you make a request in the application layer, and then it goes down and do some compression and stuff, and then sends data to the router goes to the cloud, and the cloud, that's what you mean? Isn't 7-Eleven? No, it's the 7-Eleven worker who called me and said, where do you live, so that I can deliver the water. I said I live, fuck again. Okay. Long. Are you in uni? Yeah. It's the part in a part. It's the course in the university I'm doing, but the teacher don't explain it quite well, so I have to learn it by myself again. Yeah. I just know roughly, like, yeah, but I don't know how it really works and stuff. So that's why I'm doing the practical, because computer network. Yeah, computer network. Yeah.
On the network path and then on the server. So that's why sometimes I'll have to get out a big piece of paper, draw out all my capture points, take a look at the sequence numbers, and then track them through the system. For the more intermediate advanced people that are watching right now, a nice thing, just so you know, because I have been asked this several times on my channel, and I've seen it on the industry, this sequence number raw, like what's the practical use of having it? The nice thing is that this number will live through a NAT or even a port address translation in most cases. Like if let's just say, David, that you're on the other, me, the client, I'm going through a NAT on my way to you.
Yeah.
And I have a dual point capture. So my IP changes, or even my port could change. How do I say, okay, this was the SYN that Chris sent, and this was the SYN that David received? One of the ways we can do that is by setting a filter for the sequence number. Okay, but practice and just writing it out and going through slowly like we're doing, getting practice with it. I still have more to say about the handshake. Hope you're ready for more, David.
Yeah, of course. No, this is great. Let's go deep. And I mean, I'll just say this, anyone who's watching, give us feedback. I'm trying to get Chris to give us all the detail that you don't get in CCNA courses or other materials. So, and make it real world. So Chris, share your stories. It's great to hear the real world stories.
For sure. Oh, yeah, no worries. TCP was written a long time ago, right? The RFC, you're talking about RFC 793, and it came out, I believe, September 1981. It's been 40 years.
Long time, yeah.
Let me ask you this, David. When they were sitting down and, the standards masters, the people that are amazingly brilliant, I mean, think about it. They put this thing introduced this to the world, and we're still using it 40 years later. That's incredible. But do you think that they conceived of a 10 gigabit connection across the Atlantic Ocean?
No, I mean, in those days, it's dial-up and really old stuff. So, I mean, the speeds were very, very slow. X25 had TCP at layer 2, didn't it? So same kind of idea at layer 2, just to try and make the dodgy links work.
Yeah, at that time, you're doing literally shoestring duct tape, and, you're not thinking about the speeds and feeds that we have today. So TCP was good for a while, through the 80s, through the early 90s. There were some adjustments, a few tweaks here and there on how the core protocol works, but this is what started to happen. TCP, because of some of the values that are baked into the header, started to basically, we needed more out of it. So I wanted to show you in the next section we're going to go through, which is going to be the window size and also some of the TCP options. This is where TCP has migrated and changed quite a bit from the original standard that it started out at. So far, everything that we've said is exactly the same as the original standard. But now we're going to start getting into the stuff that is more modern TCP. Let's go ahead and talk about, okay, so just briefly, okay, everybody join me back at packet 1. So we're on header length. Okay, so within TCP, the header itself, when I first send you the SYN, I basically have to make some more space in my TCP header to then be able to send you TCP options. Optional features that we may or may not be able to use on this connection. I can see that down below. You see that, David, at the bottom?
Yeah.
I got 24 bytes of options. If I don't have this header length of 44 bytes, basically I don't have enough room, top to bottom in my header, to be able to send you those options. So that's why this is an important value just to be aware of. Usually you only see this in the handshake, that the header length is this big, because you only exchange options in the SYN-SYNAC. Once these SYN-SYNACs are done, these options are exchanged, and now we're using this connection. And that's something that I really want people to take away from this. Capture the handshake. Make sure you get the handshake when you're analyzing TCP. If you don't, then we don't have the TCP options that were exchanged only in the handshake, and they're really important for fully understanding the flow. Now this header length, this is a bit of a side point, but this is a finite value. You see, we only have 4 bits to work with. Okay, so the header length can only grow to a certain point. That's why right now, one of the reasons why we've needed to move to a new protocol like QUIC is that we're starting to run out of the maximum space that the header length can be. That means that we don't have a whole lot more room for options anymore. Like, I can't come up with a new Chris option that makes TCP do some cool new awesome thing, because we're running out of space. TCP is starting to reach a bit of a limit. So that's why, and this is fuel for another video, David, but this is another reason why we're starting to see more of a move toward QUIC, because it doesn't have some of these limitations. That's all I'll say about that for right now. I definitely want to move into flags, because this is something, if you are a pen tester, if you're blue team, if you're a network engineer, if you're an application developer, whoever you are out there in the world, TCP flags are an important thing to understand. Let's go ahead and get into it. The flags field. If I like to just, when I'm learning or talking about TCP, I like to just see the hex as well. So this is telling me up here, this is just the overall flag part, this is a flag part of the header. And this is just telling me that this is a SYN. The reason, if I take a look at all these zeros,
God
false, 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 1. So there's the SYN bit is set. That means that this TCP station or whoever's sending this TCP SYN out is telling you, or me to you, David, I'm saying this is a SYN. It's not a SYN-ACK. I'm not using the acknowledgement number because if you notice up here, you can see on the original SYN, my acknowledgement numbers are 0. You haven't sent me any data yet. You haven't sent me your starting sequence number. I have no information on you, David, at all. In this SYN, I don't even have the ACK bit set. I have no, this is just basically space. It's just all zeros over there in the header. There's nothing going on in the ACK number. So SYN, that's it. That's common to see in the first packet of a TCP handshake.
Yeah, makes sense.
Yeah, I don't need any of these other things. Now, there are some other uses, obviously, for these other flags. Let me just go over real briefly. You're rarely going to see reserve. I don't even know if I've ever seen that in the wild. Nuance, I don't even think I've seen it in the wild. One time I've seen the congestion window reduced, practically used, very rare. You'll often see this be 0. ECN echo, explicit congestion notification echo, not sent. Again, not something you're going to see often. Urgent, you're not going to see often. So as you're learning TCP, just for now, let's just skip over these first 5. These bottom ones are you're going to be spending most of your analysis time. ACK, push, reset, SYN, and FIN.
I think that's what's great about what you're sharing, Chris, because you do this all the time. You know, it's one thing to learn at a book, and a book can teach you all these flags, but what I really like about what you're doing here is you're making it real. So let's focus on the important stuff like you're doing.
Oh, for sure. I mean, when the one time that I had to do some deep troubleshooting on the congestion window reduced aspect of TCP, you know, I got out that Stevens book, the TCP IP Illustrated Part 2, and I had to dig into the protocol. So just for the viewers, as you reach the boundaries of what you're comfortable with TCP, that's why we have that reference material, right? That's when it's nice to have a book. That one header value you rarely see, or if you're just learning a new aspect. Myself, I'm a student of it too, so don't be afraid to have those manuals around. But absolutely, these bottom ones are where you're going to see the most action. So let's do this. Let's come down to packet 2, and now let's notice here. So this is also a SYN, but this time the ACK bit is set. Now and forevermore, throughout the lifetime of this TCP connection, we will always see the ACK bit set. I will always be using the acknowledgement number. That's now useful. So the only packet in a TCP thread that does not have the ACK bit is the very first SYN. After that, ACK is always set. That is unless there's a few one-off scenarios. If I'm dealing with a reset that doesn't have the ACK bit set, or there's some very, very niche-y things, but most of the time, David, you're gonna see ACK bit set for every packet. The nice thing about understanding these is that we can start to set filters. We can start to go, I wonder how many SYNs I have in my trace file. Well, all I gotta do, I can just come down here to the TCP header. I just right-click this guy. And if I select the SYN bit, you see down here on the lower left, tcp.flags.syn is down here.
Yep.
Wireshark is telling me, hey, if you want to filter for that bit, this is your syntax. It's kind of a cheat sheet. It's a built-in cheat sheet. If I ever want to filter on that, tcp.flags.syn. So now I can come up here to my display filter, tcp.flags.syn equals. Let's make it a 1. Cool. I have 2 packets that met that filter, SYN and SYN-ACK. Both of them have that SYN bit set. Okay? All right, so flags. Now, as we go forward in our series with TCP, deep dive into TCP, we're going to be covering some of these other flags. We're going to be covering FIN. We're going to be talking about what is a push bit, what's a reset, how does that work. But for now, since we're focused on the handshake, I'm just going to keep moving and just leave it to the SYN-ACK. That sound good? Window, the dreaded TCP window. How does
Hope you're going to explain this. Yep.
When I first start, let me come back up to my first packet of SYN. All I'm doing, David, is I'm just giving you my starting TCP receive window value. What is a receive window? It's basically a receive buffer. I'm just telling you, David, don't send me at once any more than 65,535. If you have a gig to send me, you can send me 65,535, but you have to wait until I ACK that data. You get those ACKs, you can send me this next block. This is why window size historically has been a bit of a limiter when it comes to throughput and how much throughput TCP can take advantage of on the network. A lot more to say here, but I just want you to keep it simple. I am just telling you how much you can send me at once, how much data I can receive at once. Now, notice there's another value here. Okay, so that's my TCP receive window. But there's another thing here, calculated window size. All right, so now we're starting to cook with some gas. It didn't take long for TCP to basically, I should say the network to outgrow TCP. Because, okay, right now you're in the UK, I'm in California. If I told you to send me a 1 gig file with all the latency between me and you, but you can only do it at 65.535, do you think that would take a little bit of time?
It's going to take a while.
Problem is we have to eat the round trip for every single 65K you send. All of that latency is what's going to destroy our throughput. If I told you, hey, David, I've got a 1 gig receive buffer and you've got a 1 gig file, fire away. Like I've got this huge swimming pool behind me. I like to use water analogies when I'm talking about these things because water through a hose is kind of easy to understand.
Yeah.
If you have a swimming pool to send me and I'm on the other end of a 100-foot garden hose, but I only have a little shot glass or a teeny little glass to receive data into, you got to send me the whole swimming pool 1 shot glass at a time. David, how long does that take?
It's going to take us a long time. Yeah, very long time. It's crazy.
And you have to wait. You can't send me any more. You send a shot glass down that hose. I catch it. I catch the water. And then I say, all right, David, got it. Send me the next one. And I dump that shot glass into my swimming pool. And then you send me the next shot glass. Literally, this is what we're trying to do. Obviously, the choke point here is my shot glass. It's just too small. So,
and if you lose any of that, then you got to resend it.
Yeah. If I lose a drop, then I say, David, hold up. I lost that one little drop. You got to send that back over. Right, so that's the idea behind a window. Now, it didn't take long for that to become a throughput limiter. It wasn't bad. See, if you and I were on the same network switch, let's just say there's no latency. We literally are attached to the same network switch. We have microseconds of delay between me and you. The window size is not as big of a deal because you start sending me that 65K and I'm already beginning to receive it before you're even done sending it. So I can give you immediate feedback like, David, thanks, David. Yeah, like, keep sending. So that window size doesn't become much of a limiter until we have latency and we're on the other side of the pond from each other.
So does it always start at 65,335?
No, it doesn't. That's operating system or rather stack dependent. Whatever TCP stack that the operating system is using will have a starting window size value. Now, keep in mind, there's a bit of a caveat here, and this is, we're going to get into a little bit more of we're definitely getting into the weeds here. I'm saying my starting value is 65,535. One of the reasons why I have to use that value, I can't go any bigger than that, is because here's the thing. How many bytes do I have highlighted over here? 2 bytes. The TCP header is now limited to those 2 bytes. I can't grow beyond 65,535 with the original TCP spec. I cannot tell you a larger number. This is why, and we're going to go ahead and this is why we're going to do this now because it makes sense to put it here. If I come down into options, notice one of the things that I tell you, David. If I come down to window scale, this is an option that came around later. We ran into a bottleneck with 65,535 bytes. We needed more out of TCP, but we were limited by the header space. So the window scale option was introduced into TCP. Now, what is this? Basically, Wireshark does the messy math for us. Basically, if I'm saying, okay, window scale is the option, the length of this option is 3, blah, 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 blah. Shift count is 6. Basically, sorry for the math, everyone, but 2 to the 6th power. Okay, we're at 64. Wireshark does that math for you. Basically, Wireshark is saying multiply by 64. I'm offering this to you in the handshake. I'm saying, David, when you see my window size, take that value and multiply it by 64. And that will then be my calculated window size. Now you can take 65,535 and multiply it by 64. That's my true window size. But I only tell you that in the SIN. Here's the thing though, check this out. There's our window scale, all right? I'm telling you, David, I wanna use the window scale option because this 65,535 thing is for the 80s. Like that's so long ago. Like I wanna actually move some data. I wanna throw away this shot glass and I wanna bring out like a gallon jug, and then you can start to send me water at a much higher rate. Or forget the gallon jug. I got a huge 10-gallon barrel over here.
Yeah.
So if you send me 10 gallons of water at once, I'm gonna catch it all without missing a drop. I'll dump that into my pool and you can get going with the next 10 gallons. I can only use this though if you know what a window scale is. What if I'm talking to maybe a TCP stack on an old printer from the early 90s and that has no idea what a window scale is? Or, much more realistic example for you, you've ever heard of an IoT device? My doorbell, my LED, like my smart ceiling, my this, my that. A lot of those have a very low-end, low-power TCP stack on them. They're not really, they don't have to use a lot of these heavier features that typical clients and servers do. So I challenge this to the audience. When you're looking at TCP handshake specifically with IoT devices, check out the window scale, not just you to that device, but also the device back to you. Let's see what David did. Let's go to packet 2. Let's come down to David's options that he sent me. All right, you're saying window size 65,535, wonderful. Window scale is 9. Okay. So David, you've got some real buffer that you can use.
It's a server, isn't it? So it must have.
Yeah, exactly. So shift count 9, 2 to the 9th power. You're telling me not only can we use window scaling, but when you see my window size, go ahead and multiply that guy up. Multiply it by 512. And that's my true window. So what just happened? I told you, hey, David, I got this shot glass, but if you want, we can really get some, we can do some heavy lifting here. I've got a 10-gallon barrel over on my end. So although it looks like I have a shot glass, go ahead and send me the 10-gallon barrel. Just multiply it. Now you came back and you told me, awesome, we can use these barrels. Forget, these glasses aren't doing the work we need to do here. I got a 20-gallon barrel. Here's the thing about servers, and you said it well, and this is what you commonly will see. While servers, they have a lot, a lot of times they have a bit more resource on their end to do some heavy lifting. In many cases, I'm not sending data to a server. In many cases, though, you're going to see this on a server where it's got a larger shift count. It can do this multiplication. But if you think about it, again, I'm asking for your data in your swimming pool, David. You send it across to me and I'm catching it. As a client, a lot of times we're asking for data, sending data up. I mean, I can send data to a server. I can upload things. Absolutely. But as clients, a lot of times we're asking for data. So it's not unusual to see the client have a pretty large window that we actually take advantage of. I'm not going to send you 20 gallons to your barrel, right? But what do we learn here? In our handshake, we have options. In this case, I offered a window scale to you and you responded with a window scale back. This means, David, we can use TCP window scaling. If you did not respond with a window scale, then I don't get to use this option. So what does this mean? Guess what? Sometimes I'll have my clients send me a PCAP, or maybe the good viewers out there, you've seen a PCAP and you've come down to, I'm doing this at random, everybody. Let me come down. I'm just going to pick packet 8. And let's take a look at the window size. The window size is 131. This is from server. So David, you to me, you're saying window size 131. Don't send me anything larger than 131 bytes.
Yeah, it doesn't make sense because we went from 65,000, doesn't it?
Right, yeah, exactly. Because we got the handshake, Wireshark can calculate the true window size for us. So yeah, David's saying 131, but we have his multiplication factor. We can multiply this by 512, and the true window size that David is advertising is 67K. The reason why I show this to you, and for the viewers out there, is sometimes I'll get people, they'll send me a PCAP and they'll go, oh, Chris, look at this window size coming off of this server. It's 131 bytes. This must be the reason for my bottleneck. And I go, well, did we get the handshake? Do we know what the multiplier is? Because odds are beyond likely that that server is not genuinely dealing with a 131 byte receive window. Instead, we're using window scaling. And when we don't capture the handshake, if I started capturing right here, David, on packet 8, we wouldn't know what the multiplier is. So Wireshark would just say, it would have 131 here, and it would go,
Yeah.
I don't know how to multiply this, so this could be true, right? Questions on that? Let me back up to the handshake while you're...
You tell me your window size and I tell you my window size. And that's the maximum amount of data that I can send you, or that your buffer can handle, sorry. Does that scale as like during a session? Do we start with a small window size and then it grows, or how does that work?
That's a good question, yes. So that's also operating system dependent. A lot of times window sizes are dynamic and they will grow depending on the application and how much perceived data that I have coming in. So for example, if I do a get on web, typically a web application, okay, I'm bringing data in. A lot of times what you'll see the TCP stack do is it will grow this window size. This is not this finite number that's always static. In fact, let's do this. Let's go to our calculated window size. We're going to right click this and we're going to add it as a column. And what I want to do is I'm going to come over here. Now this isn't a very long trace file that we're dealing with, but you can see how, okay, I sent you 65,535, you sent me back 65,535. And then in the third packet of the handshake, this is the first time that you actually see me use, or Wireshark use this calculated window size. Let's look at the third packet. You see my window is now 2052. Well, we know that's not true. We've exchanged the window scale. So now Wireshark knows how to multiply this. And you as well know this, David, because you're the server. You heard me tell you, you know how to multiply it by 64. Now my calculated, my actual window size is 131,328. This is another reason why I always right click and I use calculated window size, not the true window, because the true window is so low and it's not the real number. The real number is this one. Let's just head check something here. Let's come down. So let's see what this number does. And this PCAP isn't super good at teaching this aspect. We definitely will be getting to this on a future video with a PCAP that we'll be troubleshooting with. But notice here it drops a little bit, 138.16, and then it drops down to 129.856, and it comes back up, and then it drops a little bit. You see, this number is always going to vary a little bit. It's always going to kind of float. What I don't want to see, though, David, is basically if I come down to packet 7, you see how we do drop just a little bit?
Yeah.
So what I told you is, okay, I've got a 10-gallon bucket. Well, you sent me, let's just say you sent me a 16-ounce glass of water, and that comes dripping into my bucket. Now the application, I'm able to dump that into my swimming pool. Let's just say, due to the stack and the interaction of the application, I only dump, you sent me 16 ounces. Let's just say I dump 10 ounces into the pool, and there's 6 ounces sitting in the bottom of my bucket. The amount of space I have left over just reduced by a little bit, right? 16 ounces came in, I threw 10 ounces to the application, but there's 6 ounces left. So my buffer just reduced by just a little bit. That's why this number goes down. I'm telling you, David, now I've got enough room for 9 gallons and 12 ounces. I still have room, so you can still keep sending, but there is a little bit of data that's pooled in the bottom of my bucket. Don't worry, I'll deal with it on my side. I'm a client. I'm going to get that stuff to the server. Not long after that, more data comes in from you. I temporarily, again, you can see I went down to 129.856. So that just tells me there's a little bit of water in the bottom of the 10-gallon bucket that I haven't yet dumped to the application. But right after I caught it and sent you this ACK, because it's really important for me I don't worry too much about getting this to the application while figuring out the ACK number and getting you the ACK. I want to make sure that you're not going to retransmit unnecessarily. So I got you the ACK, and then right after that, you can see that my window size went back up. So what happened here is I took my 10-gallon bucket, I dumped it to the application into the pool, and now I'm back up to my full window again, all right? So it's not uncommon to kind of see these numbers float a little bit like this. And I don't think anybody out there should worry too much if you do see, a little bit of float around a common point. It could also be, after we really get cooking and moving data, I might figure out and go, you know what, 131, we got to increase this thing. Let's go up to a meg, 2 megs, a gig. It could be all the way up to a gig of receive space that I have. But this value absolutely can increase. And again, that's just stack and OS dependent. What I never want to see, David, this is the thing to really watch out for. What I don't want to see is to have this number drop, and then go down to 0. If this number goes to 0, that means my 10-gallon bucket is full. I haven't yet dumped it to the pool for whatever reason. That's a whole nother conversation. But I got a stuck buffer. Data's there. Hey, David, stop sending. And you have to sit there and just go, let me know when you got more space, Chris. That's called a 0 window.
And that's the thing you're looking for, yeah?
That's something you never want to see. If I see 0 windows, then I go, ooh, okay, the receiver of the data is stuck. That data is stuck in that buffer, and it's not clearing that buffer as fast as data's coming in. I'm going to pause on Windows because I think, maybe for a future session, for another video, we can go into some specific TCP window problems, and I can show you guys some PCAPs that I have that really spotlight this being a choke point and when to look for it when we're looking for slow applications or slow downloads. I will tell you that when anybody says the word slow, like, hey, Chris, I was trying to download this file and it was really slow, window size is always something I'll keep my pulse on. And in fact, there's even graphs within Wireshark that let me graph this out over time and show me if it ever dips. David, before we end up, there's something I absolutely wanted to make sure you knew as well. So let's go ahead and take the options. And so we've already talked about our window scale. Don't send me a segment with any more payload than this, right? So this is an advertisement of how much I can receive at once in a single segment. We'll definitely be talking about that in a future video. These numbers do not have to match. They do not have to agree. They are not negotiated. This is simply an advertisement. Don't send me anything larger than 1460. Hey, David, you're receiving 1440. So let's just go with that. We exchange that. Also SAC. So in the handshake, in the SYN. So I tell you, I can do selective acknowledgement. We're gonna get into that as well in another video. But if I do not advertise that I can do SAC, and then you come back and say, great, I can do SAC as well. Do not advertise that I can do SAC, not support SAC, then we don't get to use it.
Yeah.
Again, why it's so important in the handshake.
Chris, I think we must continue the series. I think there's a lot of stuff that we only scratching the surface. Is that right?
Absolutely, yeah.
For everyone watching, please, put your questions below. Questions relating to TCP, and I can ask Chris to answer those questions in the next video.
Chat is really bugged. Yeah. Let me see. Where is it? How to pop up? Not. Can I pop up? I guess I can't. This one. Pop up. Pop. Yeah, pop up chat. Yay. Go there. Go. Yep. Boom. Yep. Is it perfect? Can I see? Not really. Extend a bit.
They want to, I'll say this, Chris, I mean, in the CCNA, as an example, they teach a
The electromagnetic spectrum powers data transmission, but transmitting electromagnetic magnetic waves without modulation is like trying to throw a feather across a room. On their own, waves are subject to all kinds of interference. Modulating waves to a high-frequency channel is like attaching your feather to an arrow. There are different types of modulation, but before we get into those, let's refresh on some keywords related to electromagnetic waves. We know that frequency describes how many electromagnetic waves pass a given point in a second, which is measured in hertz. 1 wave per second is 1 hertz. And wavelength is the distance from the crest of one wave to a waves. We know that frequency describes how many electromagnetic waves pass a given point in a second, which is measured in hertz. 1 wave per second is 1 hertz. And wavelength is the distance from the crest of one wave to another. Amplitude refers to the maximum distance from rest position to the top of a wave's crest or the lowest point in a trough. Phase describes the relationship between the position of the amplitude crests and troughs of two waves with the same frequency and wavelength. If the peaks of the two signals are aligned at the same time, they're in phase. Now that we're caught up on vocabulary, we're ready to talk modulation. Modulation uses a high-frequency wave as a carrier signal, varying a property of that signal in accordance with the message signal. You'll probably recognize two of the acronyms related to analog modulation, AM and FM. AM radio stations broadcast at a constant frequency and use amplitude modulation to transmit their message. FM stations, meanwhile, use frequency modulation. The carrier amplitude remains constant. Analog modulation is susceptible to noise, unlike digital modulation. Digital modulation uses a modem, short for modulator-demodulator, a hardware component that allows a computer or another device to connect to the internet. It converts or modulates an analog signal from a telephone or cable wire to digital data that a computer can recognize. This is a form of modulation called shift keying. There are different types, modulating different properties of the signal. Amplitude shift keying, frequency shift keying, or phase shift keying. Let's take frequency shift keying, or FSK, as an example. To send a 1, the signal's frequency might be shifted up by 20 hertz. For 0, it might be shifted down 20 hertz. At the other end, the receiver detects the FSK and converts that to a 1 or 0, which allows a computer to interpret the message signal sent. It's almost like old-school telegraph technology. A person would transmit a message via telegraph using Morse code, dots and dashes, to represent the letters, and an operator on the other end would translate it back into letters for the recipient to read. We've just gotten a bit more high-tech since then. Learn more about how the electromagnetic spectrum powers data transmission at howdatamoves.com.
delineate.
Hello everyone.
Hello everyone.
Hello everyone. Welcome back to the next lecture in the computer network series, and we are in part 1 of framing. Framing is one of the services offered by Data Link Layer. We will start the session with outcomes. In today's session, we have 2 outcomes. We will see what are they. Upon the completion of the session, the learner will be able to. Outcome number 1, we will understand framing. Outcome number 2, we will understand framing errors. We will start with what is a framing. In the upcoming lecture, we will see framing in a formal way, but in today's session, we will understand framing in a practical way using an animation. Suppose if there are 2 nodes. This node can be a computer or a router or a switch. This is node A and this is node B. And every node will have an adapter. And this adapter only will be sending the data, whatever it receives from the data link layer, into signals. And this signal will flow through this cable or the medium. It is received by the physical layer of node B. Now the problem is, the application layer creates the data, which is a set of zeros and ones. Then it goes to the transport layer. In transport layer, it is going to add some set of zeros and ones. It is then handed over to the network layer. In network layer also, it is going to add network layer header. We will call it as a packet. So again, it is a set of zeros and ones are added. And then it goes to the data link layer. In the data link layer, set of zeros and ones are added in the header part, and the set of zeros and ones are added in the trailer part. So we have a complete set of zeros and ones, which we call as a frame. And the set of zeros and ones are packed into a frame, and these frames are understandable only by the data link layer. As far as a physical layer is concerned, the frame, it is a set of zeros and ones. The physical layer takes every individual bits, say 1 or 0, and converts it into equivalent signals and sends it. So in the physical layer, it doesn't know anything about the frame, but data link.
This is going a little bit quick now, but it's just so game over for this domain. So I mean, we can play around for ages here, because it takes a little bit of time because it needs to create the problem.
In this video, we'll show you how to manage your caption settings when watching videos on your computer. Let's start with turning captions on or this icon and go to the font size. In this
layer only deals with the frame. Whenever the zeros and ones are sent to the receiver, the receiver collects all the zeros and ones. So the physical layer of the receiver, that is this adapter, collects all the zeros and ones and it has to construct the frame. But the problem is, how do the receiver know that this is the frame? Say for example, this computer is going to send 500 bits of data, where 50 bits of data belong to frame 1. When 50 bits are sent, all the 50 signals are received and the receiver's adapter receives all the 50 signals. And how this receiver knows that up to 50 signals are frame 1 or up to 50 bits are frame 1? And this is the problem, and we are going to deal with this problem and with a solution. And we understand that between adapters, bits are going to flow. Fifty bits are frame 1, and this is the problem, and we are going to deal with this problem and with a solution. And we understand that between adapters, bits are going to flow, and between nodes we say they are frames. Bits flow between adapters and frames flow between hosts or between nodes. We will see an animation now. Suppose there are two computers. Let's say these two computers are happy computers. Why? Because they are ready for data exchange. When the sequence of bits are sent by the sender computer, that is this computer, how does the receiver computer understand frame 1, frame 2, frame 3, etc.? Before they start the communication, they mutually agree upon a protocol, because protocol defines the rules and regulations that governs the data communication. So here also the protocol defines a rule. Let the rule be, let the start of the frame and the end of the frame be 11011. When the sender computer receives a packet from the network layer, it is going to add a header and the trailer. In the header, it is going to add this information, that is 11011, and in the trailer part also it is going to add this 11011. There are other informations are also added with the header and trailer, but I am concerned only about the start of the frame and the end of the frame in this lecture. Let's assume that 11011 is the start of the frame and 11011 as the end of the frame. Let's see whether these two computers are agreeing upon this protocol. This computer is agreeing upon the protocol, and this computer is also agreeing upon the protocol. Since common protocol is there between both the sender and the receiver, now this communication can be effective. Let's say the sender is going to send the data. If you notice, the sender is creating the data and the frame. Now this is the data. data that is generated by the sender computer. We can notice that this is the start of the frame and this is the end of the frame. Let's say this is what the information we receive from the network layer, that is the packet, and with the packet it is going to add some header and the trailer, and this is the start of the frame, it is 11011, and this is the end of the frame 11011. When the data is accepted by the receiver, it understands that this is the end of the frame and it says the frame is accepted. Why? Because this node also knows that the start of the frame is 11011 and the end of the frame is 11011. There is a serious problem here. Let's see what's that problem now. Can you figure out any problem in this scenario? Let's say this is the data generated by this and this is what the frame is, because we have a starting sequence that is 11011 and we have an end sequence, this is 11011. Can you notice there is a problem here? If you want, I will give you a clue. And this is the problem actually. There is a sequence that is 11011 in the data part also. According to this sender, whatever it has received from the network layer, it adds the start of the sequence and the end of the sequence. But this data is nowhere related with the data link layer. And we can understand from the scenario that this is the end of the frame and this is the start of the frame. And this one, that is this 11011, is the data or the payload. There is a data which is resembling the start of the frame as well as the end of the frame. So when the receiver computer receives this information, it understands that this is the end of the frame because the adapter of the receiver receives continuous zeros and ones. Whenever it receives 11011, it understands that's the start of the frame, and it understands this is 0, 0, 0, 0, 0, all these are data. And whenever it receives 11011, it understands this is the end of the frame. So according to this receiver, it understands this is a frame. Actually, this is not the frame that was created by the sender. When the receiver constructs this as the frame, this is what we call as a framing error. We don't expect our receiver to create a frame like this. This is the problem, because if we say that the bit sequence is the start of the frame and the end of the frame, and there are chances for the same sequence to appear in the data part also or in the payload part also, and this framing error has to be handled. And we will see in the upcoming lectures how framing errors are handled in the protocols. I hope you guys have understood what is framing and framing errors. I hope you guys enjoyed the session and thank you for. In the previous
yeah, I guess thanks everyone for watching the stream. Highly appreciate it. I might have to head out now because I will go exercise, and apparently there's something wrong with the thing. Okay, there we go. So yeah, everyone, thanks for the streams, thanks for watching, and yeah, wait, why this is so bright? Never mind. I see. So thanks everyone for watching, and yeah, I'll head out. Bye bye.